Hello, my name is Jan Brugard. I'm the CEO of Wolfram Math Core. During this talk, I will present the Wolfram hydraulic library and the new library store. For those of you that were in this morning talk, there was a lot of problems with the projector. We tested here. It should work better now. I will present the Wolfram hydraulic library. It's one of several new libraries that we're adding to System Modeler. And the library is designed to be as easy as possible to use and have a comprehensive set of components. I will go through and show the different types of components. But it has different hydraulic motors, cylinders, actuators, valves, and so on. But before we go to the library itself, I want to start to present the library store and what that is all about. So with the launch of System Modeler 4, that will be launched very soon, we'll be launching a new library store. That's a place where you can get add-on libraries to System Modeler to add functionality. This is a screenshot, an early screenshot that we made during the process for the idea of how the library store would look like. So it's not exactly these libraries that will be available from start, but most of them will be, and others that are not shown here will be, well, a few will take a little bit longer. So you can see, for instance, we'll have the hydraulic library here, and which is a paid library, so it states a price for it. While free libraries that you can download, like the Planner Mechanics that I presented really quickly this morning, is a free public domain library, so that is just a download away. You don't have to pay anything. So depending on the developer, the libraries will come at a cost or be free. So who is producing these libraries? Well, in the case of the Wolfram hydraulic library, it's developed by ourselves. But most libraries will be produced and are produced by users. So if we take, for instance, the System Dynamics library here, it's produced by a professor in Switzerland, François Cellier. While the Smart Cooling library here is developed by the Austrian Institute of Technology, and so on. This means that as a user of System Modeler in the future, you will be able to add libraries, and they will be and ship them through our library store. Meaning that any user around the world will be able to get your library from there, either paid or free. When we're using the Modelica language, it is already available a lot of libraries there that you can add to System Modeler by other means than using the library store. But the benefit of using the library store is that we have really tested them with System Modeler so they work well. We have gone through the library so the documentation is good on par. Depending on if it's a commercial or free library, we will set different levels for that, of course. But we do make sure that they are well-structured libraries. And we make sure that we will have good information on the web page. For instance, this System Dynamics library here, you will have an introduction on what the library is all about, what are the key features, and you will have links to blogs, to industry examples, to courses, and so on, to learn more about the library. And of course, get all the requirements and so on. So the idea is to gather everything and make it as easy as possible to access it. And one of the new libraries is the Wolfram hydraulic library. And before I start to use it, I just want to mention a couple of the key features. So the library, as I said, is designed to be as easy as possible to use. And it's a hierarchical large-scale library with a lot of different components. And as you might guess from the name, designed to model hydraulical system. Of course, not hydraulical systems as standalone systems only, but also together with the rest of the system, the mechanical part or whatever part you're connecting it to. It includes standard media components, meaning that you will have different media for different types of oils, water, and etc. and a bunch of examples illustrating how you work with a software. And I will show one of the included examples during this presentation. All the icons use standard DIN ISO 1219 standard representation, so it will look like the standard representation of hydraulic systems. And you can combine this with any other Modelica standard library components, of course. So where would this be useful? Well, in quite a lot of different industries. This should not really be there. You could use it, of course, with automotive applications. It's really relevant. Avionics systems, construction equipment, mining, etc., etc. So there are a lot of different industrial fields where hydraulics applies. Basically, anything mechanical that moves has some kind of hydraulics or sometimes pneumatic system to move it. Okay, so now it's not online yet, so I cannot do it from the web page. But suppose we were on this library store page here. This would have been the Wolfram hydraulic library. What we would do there is to click this, which is not a free download, it's a paid library. So you will get there, get to the web store, pay for it, and you will download something called an SMA file, which, if I go there, will be something like this. And it works similar to any software you would install, that you double-click on it, and you get to the standard activation system of System Modeler and Mathematica, so you will recognize how this works. So you will tell, okay, this is the library, install. It will ask you to activate it. I will have to activate it manually here. And so I cheated. I did this beforehand. I have the activation key. And this is typically what you do online, so you'll get this directly through the online service rather than having to go manual, but you can go manual, make a call, or do it by email and so on to get the information. You activate the library, and once you activated it, you can see here that it's added to your system. So what does the library include? Well, we can open it by browsing here, and we can see that the first package we have is an example package. If I browse here, I can see that we have examples for all different sorts of actuators, like we have translational, rotational, we have multiple actuators, flow control, accumulators, and so on. And if we open one of them, let's say the rotational part here, we can see that we have, in this case, 3 different examples. Before I start to show the examples, I'll show a little bit more about which kind of components we have. There are all sorts of directional valves, flow control valves, pressure control. So we'll look at the flow control. We can open that and see that there are several different types of hydraulic valves included in the library. There are cylinders, different types. We have different restrictions, and so on. So it contains basically all the hydraulic components you need to compose most of the hydraulic systems you would like to model. If I open an example, well, let's do that. We can go here first. If we open this example, which will be a servo with control, let me do this. There is a small thing here with the activated version, so I need to reload the library right now. Tomorrow that will not be needed any longer. So let's find out this one here. There you go. And I'll open the example, the first introductory example for us. Open. Take the servo mechanism here. To open among my user classes here, I can go down and open the model. So here's the model. One of the new features in System Modeler 4, by the way, is that we can now go and say view and choose a presentation layout to make it easier for you to see it in a larger scale. So now we have the presentation layout, and we can try to understand what this system does. So basically what we have is a mass here that we're trying to move according to a certain pattern. That pattern is given by this input step here, so we're basically saying that we want to move it from this position to that position. In order to accomplish this, we have a hydraulic system. We have 3 tanks. Look at them here. And we have, for instance, a motor here. The motor will build up a pressure, and depending on this pressure, we will then be able to move the cylinder back and forth. Of course, that depends on how the valve is actuated. So let's look at the help here. How does different components work? So in the help, there is a good explanation of every component with the illustration of first the icon itself here, and then how a typical valve of that type is implemented. So we can see here basically that if we are in the neutral position, which is the middle one here, we will have the P and T port connected directly together. That's what's illustrated by this one here. So P and T, these P here and T here are connected directly together at default state. And A and B are not connected at all. And then depending how we actuate this, we will get different kind of connections. So in the help, we can also see whatever components are used to model this. So we can open the list of components. We can see that this has, like this. This has several different components like the medium, the spool, and so on. So we can click down here and look at that, for instance, the medium, and see how is the medium defined, and so on. Or if we want to learn more about how this kind of example is used, we can ask it, in which examples of the library is this component used? So we'll look at that, and we will get a list of used examples, examples where it's used. For instance, load holding circuit here. Yet again, it's described a typical example, how to use it, and so on. And actually, directly, this is also new for 4, directly from the documentation, you can click play to simulate the example with its standard settings. So you don't need to find it in the browser or anything like that. If you want to find it in the browser, you can just click on the link here. And if we go to the model editor here, it has opened this new example for us. So everything is cross-linked right now from 4, and you can find easier the example. So let's go back here and see if we simulate this. So I simulate this example, and once I've done that, I get access to all the variables. For instance, the input was our step source, which I guess, where is it? Start step. This is our reference signal that we want to follow. And if we look at the position now from the load, we can see how it moves. Of course, what we're interested to look at when we're looking at a hydraulic system is not only the result, what's the movement of what we're actuating, but we're interested to look at things like pressures in different parts of the system. So we can look at the chamber pressure, for instance, of the chamber A and the second chamber, and so on. So this way we can see all the dynamics internally in the hydraulic system. As you might have noticed, there are quite a lot of variables available, so sometimes it was hard to find the right variables for you before. That has been simplified with 4, so if I go to find options, I can actually say I only want you to list anything that is a mass in kilograms. And then only components that have anything with mass in them will be listed. And I can open the mass here, and it kind of will be a boring plot if it's fixed, and of course, and so on. So that's a small addition to make it easier to find the result. Now, we have made this simulation. We have seen that it moves, it actuates the cylinder the way we want. But I want to show another way to actually do this, and it's connecting it to Mathematica. So I'll load the link to Mathematica, make a plot here of the mass position and the valve state. So the valve state is basically telling us how the valve is moving from the 3 different positions, right? So here we can see it as a plot. And you can then understand, okay, it's on the left-hand side, -1 is the left-hand side, then it moves somewhere in the middle to go to the right-hand side, and that will change where we will have the flow. But there's an easier way to understand how that goes on. We can simulate this within Mathematica with WSM Simulate, and then we can create an animation. Because diagrams now can be defined so they are possible to animate. So we look here, and we can now see if I play this, and we could have, of course, add the actual plots and so on. If you look carefully here at the blue dot here, it shows at every single point in time the position of the spool. And likewise, we can see the position of the cylinder as a function of time, how it moves there. So this way, it's easier to see how the actual system works. And we can connect it to do any animation, as I said, with including the actual plots of the pressures and so on. So this very small example, of course, it's interesting with the small examples, especially for learning how to use it. But at the end, you want to do something larger, some real scale example. So for System Model 3, we had this model up for download at the industry example pages. It's an excavator model, which looks pretty nice, actually, if the connection is with us. See here? There you go, hopefully. So it looks pretty nice. The only problem with this is that it only included the mechanical systems, and the way we moved it was by setting, basically force it to move without any real hydraulic system behind it. Now, with System Model 4 and the new library, you can add the hydraulic system to it. So let's look at that. I'll open the example. That was not the right one. Then should be this one. Okay. So here is the example, and this is how, let's open the help. This is how the example looked like before, where we could dig into the different components, and it would only be a mechanical system with different 3D mechanical parts, and as I said, it would be actuated by input table setting fixed positions for the system. Now, and this is under development, this example, so it's, I won't show the finished version. But now what you can do is you can actually add the hydraulics to it. So let's do some test assemblies here and open full excavator test here. Presentation layout, there you go. So this is only the part of the actual arm and bucket and so on. But this is the moving part, the thing that we're interested in. And we can see now that we have these components, which were the mechanical components modeled since before, and we have added hydraulical systems to it. So in each of these, we can click in and see that it's actually a similar system to the small servo mechanism we had. There is some different things like these check valves here that which have an assistant pressure in order to kind of give a smoother movement for the hydraulic system or for the bucket. So the hydraulical system will typically be something like this. We connect several of them, and we get this excavator. So let's simulate that. We build this example, and when we simulate it, in a while I will show a new feature. So while you're doing this building process, converting it to C code, you have to wait for that to finish before you can do anything else. Before, actually, you have to also wait afterwards when you started to simulate until the simulation ended before you could do anything else. It was locked. It would lock the software for any other operations. But now, hopefully, if it simulates, we can see that this takes some while to simulate. You can see the progress here. But it doesn't lock our system. Let's just restart that to give me more time to do other stuff. So we have the simulation going on, but I can actually continue using the software. I could open new models. I could do whatever like. Let's say go back to this custom window layout and open the Hello World model to open something very simple and choose to simulate that. So now we can see that this is a simulating. Now they ended both. We can work with these things in parallel. And when you start with these larger systems, as we will start doing with the hydraulic components, this will be very useful because you can start one experiment, do the next one, start that one, and so on, and keep working. So let's look at the results here from our excavator. Look at the animation. We have it here, and if I select a component, let's say the bucket here, it will select the same component in the component view, so I know where I can find the corresponding variables to plot them. But in this case, I'll be satisfied with just plotting it and see the movement. So in this case, we have the excavator doing its work by actually being actuated correctly by the hydraulic system. And just as we did for the servo mechanism, we can now dig in and look at the pressures and so on to understand the operation of the system. Another example, I might open the example first, is with avionics. And let's open that. Flap system failure scenarios, it says. So what we have here is a Cessna Conquest 441. Looks like this. You should be a shortcut for that. Probably there is, but I haven't learned by now yet. Okay, so here we have the system. We have a pilot. We have the electrical system, the hydraulic power, the flaps, landing gear, and so on. And each of these consists of different components. For instance, the electrical system, of course, has mostly electrical components with wires and so on, and gives the logic for how to operate the system. While the hydraulic power and the flap system, if we look at them, have all the hydraulic system to actuate the flaps. In this case, we see that we've added pipes also. In any system where you have longer pipe systems, it's important to have the loss of the pipe included in the model, so that's something you can do here. And it's a rather complicated hydraulic system, so I will not explain exactly how it works, but you can see here that you can add that, and if we look at the flaps, it also has a hydraulic part in it. The reason why there is one hydraulic part in the motor is because that's the common hydraulic part that is used both for the flaps and for the landing gear, while the landing gear and the flap have parts also that are just for those parts, and this is what you can see here. I could, of course, go on and simulate this just as I did with the excavator, but I will just talk about the scenario where this would be useful instead, in order to kind of give some kind of sense. What do you want to use it for? So if we look at the Cessna and the flaps basically have 4 positions that they can operate in: 0, 10, 20, and 30 degrees. And you use them for different parts of your of your flight. It's when you're taking off, when you're approaching, when landing, and 0 when you're cruising. So depending on what you will do, the pilot will give it a signal, this is what I want to do. It's electrically operated and hydraulically actuated. So it's important to be able to combine the electrical system with a hydraulical system. And we already saw the model. Let's look at the top level again. Yes, remain. So we have, as I said, electrically actuated. The pilot tells it what to do. Then the electrical system will tell the hydraulical system how to actuate. If we would look at a nominal simulation for this, which means a simulation where everything is working fine, we have it here. It's pretty simple, this simulation. What we have is the command from the pilot, where the pilot basically moves the command for the flap, and the flap will change position from 0 to 10 degrees like this. Okay? So it's very simple, this scenario. And then you could look at the pressures and so on and understand the system better. But more interestingly is what happens if you start to add failures to your system. So in this example, we have added failure modes for the different pipes, for the different electrical parts like the spool here and so on. And then we can use Mathematica to programmatically go through and test different scenarios, different combination of failures, single failures, double failures, and so on, and look at what's happening. And I'll choose to show you the failure of an electrical failure rather than a hydraulic failure, because it's kind of easier to understand what's going on with that failure. And it's kind of more spectacular when you talk about it. So suppose we have an electrical failure here in the spool that actuates this valve, meaning that the valve will not move when we try to move it. What would happen? Well, if we simulate a scenario here where the curve here, the red here that you see, is the command from the pilot, the blue is the actual position of the flaps. We can see that when he starts, when he's about to take off, he wants to have it at 10 degrees. And the flaps move to 10 degrees. Then, once he's up cruising, he wants to go to 0 degrees, but that doesn't happen. The flaps are stuck. Now, he comes to after a while, it doesn't really matter too much. It will cost more energy to fly, but he can still fly. Now it's time to land. And then he wants to change to 20 degrees. Still, nothing happens. And that's for the approach. Then at the actual landing, he wants to go to 30 degrees, and still nothing happens. So this is critical suddenly. He can still land, but he needs a longer runway. If he's lucky, he's at a big airport and can make the landing. If he's unlucky, he's in big problems. So by doing this simulation programming and finding these types of scenarios, we can identify, okay, this is a high-risk scenario. This should not happen. So the consequence of this for the developer is, first of all, to make it as sure as possible that it doesn't happen, of course, that it doesn't fail. But you can never be sure that that doesn't fail. So what do you do if it fails? Well, you put some measurement equipment, sensors, so you know to give the pilot a signal at least that he knows that he has this error. Even more so, you can actually then, once you discover the error, what happened there? Let's see. Once you discover the error, you can actually have recovery instructions. In this case, and it's probably planned from the beginning of the Cessna that they actually designed it with some intelligence, they have realized, they have found a system that even if we have this shortcut, we can tell the pilot that if he does a certain sequence command here, this is the flap control, he gives it 2 extra pulses, which basically he would not do typically. Then his landing procedure, his starting procedure will work exactly the same as before. And exactly as before, there will be a problem. It will not get from 10 to 0 degrees. It will not go from 10 to 20 either. But it will actually be possible to switch it to 30 degrees. So suddenly has a safe way to land. And the combination now of the hydraulic library with Mathematica makes it possible to build this system, build different failure scenarios, and then programmatically go through in Mathematica to identify what is it I'm failing with and how could I prevent it from failing. So with this, I think I was kind of 10 minutes, I guess, faster than planned. Thank you very much.
Okay. So perhaps we can use the remaining 10 minutes to deal with any therapy that somebody needs to go through after talking about planes and...
Yeah.
I have a mild fear of flying, and now it's moved from mild to... maybe I'll stay another night or a week.
They have good safety systems.
Yeah, that's all right. I'll just ask British Airways if they've spoken with you. Okay, so we have an extra 10 minutes. So if there are any questions, now's the time to go crazy with questions. Yeah, one over here.
I have several questions. One is about the library itself.
Yep.
Some years ago, we can mention we have a hydraulic system in this room. If you look there, we have nice sprinklers. Sprinklers are supported in that library. Are there elements for sprinkler systems, sprinklers itself, or alarm clocks, or several other things?
You don't have the sprinkler themselves, but I assume they could be modeled using some kind of the standard restrictions, but there's not specifically a sprinkler. And for the alarms, you have measurements and so on, so you can measure and set sensors and put alarms on that part. So that is included.
Okay. And can I add my own components, for example, sprinklers?
Yes, of course.
Okay.
So you can do that. In a sense, you can do that even without the hydraulic library, but you will have to do a lot more work. But with the hydraulic library, you can use that to compose new components with that. It contains, if we look at the library, you really show that. If we look at the library, it has parts of it, that are components that you build up the system from. The interfaces here, for instance, have the standard ports, the standard types like that. You have static models that are base models. You have models for leakage, for friction, and so on. And those you can use to drag and drop together your new system. Or you can add your own equations, do your own completely own version. So it depends on how close you are to what's available, if you will do it drag and drop, or if you add your own specific equation.
And the last question I have, in sprinkler systems, you have pipes with several diameters. Large diameters mean high pressures for the sprinklers and high costs. Yeah. And now the problem is, can the system decide what's a good
Of course. So if let's say that you have this system here where each of these pipes are the pipes that you have in the sprinkler system. And that's actually something I missed to mention. It's much easier nowadays to find the right parameters in your model, because in the model nowadays there are specific tabs where models are where the parameters are better sorted. And here you can find that this pipe has different things like the leakage. You can set parameter for that. You can set the parameter for the environment, pressure, etc., etc. And it doesn't list actually the diameter. Should do. There is a diameter for it that you can set, and as soon as it's a parameter, you can of course set it then in Mathematica and go through set up an optimization problem in Mathematica to find the combination which is the best fit to whatever goal you have. There's good examples on the web page for that. I can point you out to those.
I had a question about the diagram, the animation of the diagram.
Yeah.
Was that being done in Mathematica Or in System Modeler?
It's prepared in System Modeler, but it's done in Mathematica. So any component, and if we let's look at the icon for this example here. So this is the icon. It happens to be a picture, but if I go to properties, I think, oh, let's do something like this instead. I haven't done this myself yet. So this is the first time. Then you have dynamic graphics here. And what you can do is you can put this as expressions. So basically, I could say that the extent of this would be minus 13 times time, which is represented by t. And then, and it could be any modelic expression, basically. So it could be dependent on the pressure or the temperature. So basically, our temperature sensors that will show and so on. So in these, you can define as function of the simulation variables. And then when you have them in Mathematica, Mathematica will use that to create a diagram.
Do you have a script interface to System Modeler, to the System Modeler? Can you write scripts?
Yeah, well, you can write scripts through Mathematica. So you can use Mathematica for scripting it. Is there a specific thing you would like to do? No? So there are, you can, if you want to have things that are run during the simulation but run externally for some reason, you can include C code, Fortran code as external code and use that as input for your model. But you can then also use the Mathematica environment if you want to script simulations, for instance, or programmatically create models. So you can kind of do whatever you like from the Mathematica environment with both the models and the simulations.
Thank you. Any other questions? Okay, so we still have another question. You're making me get my exercise today for sure.
That's good.
It's the only exercise I'm going to get this week.
One thing I don't quite understand, if I see this, I can simulate, but if I wanted to do a real-time system and have the same modeling being done, is there a way to act on events in real time and have the...
Yeah. So you can connect, basically, now when I simulate, I didn't simulate in real time, but you can set systems to synchronize with real time if you like to, and you have several ways to talk to the simulation while doing that. So you could have, one of my standard examples I haven't brought with me is a quadricopter where we have the model and then we have a gamepad to control it. So you can connect kind of anything to and run the simulation that way. And then the other thing is, once you have it, you want to deploy it into a real-time system, a hardware-in-the-loop system, then you can use the new functional mockup interface, the unit there, to use that to deploy it into the hardware-in-the-loop system.